All right, welcome to the latest Vodcast. I have a guest host today. Mrs. Ehrman's going to help out with this Vodcast because she's going to do this for her students as well. Hi, Mrs. Ehrman.
Hi, Mr. Herberton.
Great. So there are 5 types of chemical reactions we're going to go over today, and here they are. What are they, Mrs. Ehrman?
Well, we have the synthesis reaction, and synthesis means that we're going to make something out of its component parts.
Right, we combine things. How about, what's a decomposition then?
Well, that's when we start with one thing, and we're going to decompose it into different parts.
All right, break it down, all
it's
right?
the reverse of synthesis.
Oh, that's a good way to look at it.
Yes.
What's a single replacement reaction?
Oh, well, there's 2 types of them, actually, Mr. Herberton. There's one when the metal replaces a metal.
Okay.
And then there's one when the halogen replaces a halogen.
Oh, wow. A non-metal replaces a non-metal. That's
you got
great.
it.
Perfect.
Some people say it's cation replacement or anion replacement.
Excellent. Then we have double replacement reactions where I like to talk about them swapping partners, but you talk about it as being
like as part of foil.
Yeah.
Instead of doing first, outer, inner, last, you get rid of the first and the last, and it becomes outer and inner. And they change partners, and I call it the OI reaction.
I remember that from math class.
Yes.
Okay. And then finally, combustion reactions, that's burning. You guys are pretty familiar with that, all right? What's important about learning, why we need to learn the different types of chemical reactions, is that once you know the style or the structure of each type of chemical reaction, you'll be able to identify which kind it is, and from just the reactants, you'll be able to predict the products.
Yes.
That's the power of this, all right? First, synthesis, which we call combination. Here's an example. Say you take some carbon and oxygen and form one new thing, carbon dioxide. See how we combined or synthesized into one, right? Now let's look at the actual molecules, Mrs. Ehrman.
So in this one, we're going to have one atom of carbon reacting with one molecule of oxygen to make one molecule of carbon dioxide.
Yeah, notice that the carbon is now bonded to the 2 oxygens, and you have a new substance with completely different properties, right? Think of carbon. It's black and solid. Carbon dioxide's a gas. Pretty cool. All right, here's the general structure of a synthesis reaction. If I think of A and B as either being elements or compounds, what they're always going to do, you're going to take 2 things, combine them into one to make a synthesis reaction.
Right. So you're always looking for one product. One product is synthesis.
Right? Let's predict products based on a synthesis style reaction. Always remember that when you write the products, go back to your ionic formula, charges, and crossover rules. You got to have the right formula on the other side. All right? So, what do you think? Sodium and chlorine. What are they going to make, Mrs. Ehrman?
They're going to make NaCl.
NaCl, you mean, oh wait, where is it? There it is. Sodium chloride. Exactly. You know that from these 2 things, they're going to make one new one, and so that'll be sodium chloride.
But
and notice, yes.
It's not balanced. I'm feeling sort of out of balance.
It isn't.
Here.
Now, the key thing, sometimes people love to say, well, there's a 2 on the chlorine here. I better put a little 2 subscript here. Is that right?
Work. No.
Why not?
Because you can only balance chemical equations with coefficients.
Oh, I see. Because NaCl is +1 -1. So what do we do?
Well, you're going to have to put a coefficient of 2 in front of the sodium chloride.
Oh, like that.
Right.
Very cool.
Oh, man, Mr. Herberton.
What's the matter?
Your sodiums are not balanced.
Oh, I'll put a 2 over there as well.
Oh, now I feel very balanced.
Ah, finally,
yes.
Back in balance. All right, great. All right, so now everyone do the next one. You might even want to pause this for a second. Balance the next formula, equation. All right, so is this what you got? 3 fluorines, 2 aluminum fluorides. Oh, do you need anything more? Yes.
Yes.
Is that good?
Perfect.
Balanced?
I feel very imbalanced.
Right, so same number of atoms of each element on both sides. The second type of chemical reaction is decomposition.
Right, remember it's the reverse of synthesis.
Ah, so let's maybe take that salt and break it into its original components, chlorine and sodium. So it'll look like this.
So what's going to happen is we're going to split that molecule just in half. And it's going to come out with chlorine and sodium. But why is there 2 chlorines there, Mr. Herberton?
Oh, because we were trying to represent it. It's a molecule, a diatomic molecule of chlorine. what should we really be showing on the left?
It's actually another chlorine.
We should show and sodium, right? We need another sodium chloride over there. We'll work on that.
Okay,
all right?
But chlorine is a diatomic molecule.
It is.
So as soon as it's formed, it reacts with a number of its species.
Right.
So
but
that's
we had
why
to balance it up
diatomic.
here.
Yeah.
All right, good. So here's the general structure of a decomposition. Whenever you see one reactant, there's only one thing it can do. Break apart. So third is single replacement.
Yes, this is a very important reaction for us because there's other things that go along with it.
Oh, okay. Well, here's an example of a metal replacing a metal.
Right.
Notice how the zinc was on its own, so it was just like solid zinc element. And it was put, say, in a solution of copper chloride. What happened on the other side, Mrs. Ehrman?
Well, the zinc knocked the copper out of the compound and took its place.
All right.
And there's poor little copper all alone.
There. See how the zinc was on its own initially? Now it's in the compound, and the copper is left on the side. I kind of tend to call this cutting in. Oh, see, I have dance analogies for these.
You must be
so, pretty darn good. Yeah. Not good enough for dancing with the teachers, but, So, zinc, in this case, cut in. It's now dancing with chlorine. Poor little copper sitting on the side. Yep. All right, so let's take a look at a few. What's happening here? Oh, wait, I don't see a metal over here. What's going on, Mrs. Ehrman?
It turns out that hydrogen is used as a standard, and if we're going to look at a special chart, that's going to help us determine whether hydrogen is going to be replaced by zinc or not.
So in a way, it's acting like a metal in this case.
Yes.
All right, so zinc can replace the hydrogen in an acid.
Right.
Wow, okay, so that's what's happening here. Notice the zinc is now with the chlorine again, and now the hydrogen is on its own. Why is it written H2?
Because it's diatomic.
Oh, that's right.
And as soon as it's formed, it reacts immediately with another of its species.
Right, so when it's on its own, you always see it with a little subscript 2. Good point.
Absolutely.
All right, so why don't you guys try and look at this and see if this needs any balancing. All right, notice this is slightly different. Fluorine, a halogen.
This is a halogen replacement or an anion replacement.
Okay.
This time the metal... There's only one metal there, it's sodium.
Right.
But there's two halogens present, fluorine and chlorine.
Okay.
This time the halogens are going to fight it out.
Excellent. And it looks like fluorine won the battle and cut in. All right. So we need to balance it with a couple of 2 coefficients. Now we have our balanced chemical equation. All right. Next, we have double replacement. Right. Here's an example.
Well, now we have 2 compounds. And we're going to get 2 compounds in our answer.
Right. The neat thing about this, double replacement, think cation, anion. Notice we got magnesium oxide and calcium sulfide. Both have cations and anions. What happens? They swap.
Right.
Right?
They switch partners.
They do. In my dancing analogy, I call this swapping partners. So look at this. Magnesium was with oxygen. Now magnesium's with the sulfide. Calcium was with sulfur, now it's with the oxygen.
Perfect.
You just switch. It's easy. Just switch them. So here it is, the general form, A plus AB and CD make AD and CB. All right? And we call that cutting in. I'm not cutting in. Swapping partners.
Yes.
All right.
Dance partners.
Oh, there it is. I knew it was around here someplace.
Yes.
Swapping dance partners. All right. So here's another example. Silver nitrate, sodium chloride, and look what's on the other side. The silver's with the chloride, and the sodium's with the nitrate.
Right.
Good?
Mm-hmm. So the silver went with the chlorine, and this is the foil analogy.
Right.
The outer go with the outer, and the inner go with the inner.
Yeah.
But remember, the cation is always written first.
All right, so which would be the outer and inner on this one?
Well, potassium and nitrate are the outers for this one.
Okay.
Okay, and barium sulfate are the inners.
Got
for
it.
This one.
Got it.
But
and
remember, the cation is always written first.
Yeah, make sure you write the cation first, then anion, cation, then anion. That's what people don't do. All right, finally we have combustion reactions. You guys know about that.
Yeah.
Fire!
Yeah.
Woo-hoo! We love to burn things, right? Well, we're going to be very clear about what we mean by a combustion reaction. We're going to take a hydrocarbon fuel, something with carbon and hydrogen in it, and react it with the oxygen in the air.
Yes.
Right? And we call it burning, and you need three things.
Always. You need fuel, some sort of hydrocarbon, oxygen, and something to start the reaction. Because when we turn on our propane burners in the lab, they don't burst into flame.
Right.
We have to use the striker.
Right.
We need some sort of energy to start the reaction.
But once it gets going, it produces its own energy to keep going.
Right.
All right? So let's take a closer look at this. What's interesting about combustion reactions, they always produce the same two products. You take your hydrocarbon, react it with oxygen, and you always form carbon dioxide gas and water vapor.
The only time you don't is never.
That's right. We always do that. Well, there's the bell. We must be getting near the end. We'll wrap this up. No, actually, we'll have to cut this out. But let's go to the next one.
Okay.
All right. So here's an example, right?
Right.
And if we wanted to balance it, right, it would look like this. Go ahead.
Sometimes they have very large coefficients. Don't let that scare you.
Right. So now try this one. You're going to have to pause and work on it. Remember, what are the two products that will always form?
Carbon dioxide, gas, and water vapor.
Yep. All right. So the answer is this. Did you get that? Huge coefficients.
Huge coefficients.
Huge.
But don't let that scare you.
Right.
That's what happens.
All right. Well, thanks for this new double video podcast from Mrs. Ehrman and myself.
Bye.
Bye.